Well, good morning, class, or good afternoon, whatever time you happen to be viewing this. So I'm a little slow getting a lecture posted to you. It's been pretty busy here, as I trust you guys have been too. So this is slide 33 in the pumping slides that you guys have. So hopefully you can have your slides in front of you while you go through this. So let's get moving. So we're going to talk about developing system curves from field measurements here. We got a section on this. Okay, so we may have done this one in class. I wasn't sure where to start, so we'll go back through it. But before we get started, a few things to consider. We want to understand the critical parts of the system. So how do you get that done? Well, the process and ID drawings is a good place to start. You can talk to operators of the system, operators who control this sort of thing. Really, they have to understand exactly what's going on currently because they're in control of it. And you can walk down the system with your PNID and note any changes. I think we did talk about this in class, so I'm going to move pretty quick. Operators know what's going on. And note, if you have a real complex system, this simplified version of a system curve may not be adequate. You may have to go to full fluid mechanics modeling of the entire system. But for most systems that I've run into, these concepts work pretty well. Okay, so system curve, it requires to fit one, you have to have 2 points of operation, and each point is described by a flow and the required head to allow that flow to occur. So we have 2 points like that. An easy point is the zero flow, which then you try to determine the static head on the system. If there is any, it could be zero. The equation that we're going to fit is of the form H, which is total head is equal to static head, H sub S, plus a constant that we fit from these two data points, K prime, times flow, Q in gallons per minute, raised to an exponent, which will be either 1.9 or 2. So, and that last term, K prime Q to the C power, is the frictional or dynamic head. The H sub S is the static head, and the combination is total head. Okay, so for the second point, what we use, for a system that's operating, we can go to the pump and try to take measurements to determine the pump head and the flow at that point, and we use that as a second point to develop our system curve. So one approach is measure pump head at the operating flow rate and let PSAT do the rest of the work. That's the head calculator we may have looked at in PSAT. Why does this work? And it's because the operating point is at the intersection of the pump and the system curves, which I know we've said that a few times. Okay, so this is kind of redundant, so it just kind of echoes what I had said on the previous slide. And this shows graphically what this looks like. If you look at the K prime Q to the exponent term, that's the frictional head. Don't seem to be able to get a pointer moving here, so you'll just have to look at that. And then if there is a static head, it's just a horizontal line. And so the total head would be the combination of those. Or you can think about picking up the frictional curve and setting it up on top of the static curve. And then that total curve up on top represents total head. So that's not too bad. Okay, so uh, we're going to use this little simple example system with water being pumped from one tank to the other. And so you see in the suction tank, see, it's possible that we could have a gas overpressure, which would be P1. Uh, if that tank's open to atmosphere, then that pressure, there's no gauge pressure, there's just atmosphere sitting on top of it. And then you'll have the height of the water column in the suction tank to consider. We'll see, we've got a couple of slides on this. Moving on down the piping system, we're showing a suction gauge at P2 and that gauge is some elevation off of, say, the floor or a conveniently selected datum. We go through the pump, and on the discharge side of the pump, we're showing another gauge at P3, which is potentially at a different elevation. For this little example, we're assuming that the pipe sizes are the same on the suction and discharge. We go on downstream, we go up vertically, and that F for the circle indicates a flow meter. And then we go on up and we discharge into the discharge tank, which potentially has a different overpressure, which could be a P4, and then there's an elevation in that tank. So we will, that picture will appear in a few minutes, again, with some numbers, and we'll go through an example. So, but let's consider the static head term for a second. What are some sources of static head data? Well, we can measure some pressures, we'll see, or we can measure some elevations, level in a tank. We can actually go out in the field, or we may be able to get this information off of drawings. And here's an example of trying to determine the difference in elevation from the free surface of the suction tank on the basement to the discharge tank on the second floor. And so you see we can count steps. So if you count up all the steps from the basement to the second floor, we get 32 steps. 7.5 inches per step is 240 inches, which is 20 feet. And then if you look on the second floor, the fluid level in the discharge tank is 8 feet above floor level. So that adds 8 feet, but the suction tank level is 5 feet above the basement level, so that subtracts 5 feet. So overall, our static head is 23 feet here, and that's assuming that we have the same pressure, or those tanks are open to atmosphere, or they have the same gauge pressure on the top of both fluid surfaces. Another thing you could do triangulation or something from geometry, or you could count the rungs on the cooling tower ladder and then estimate any other elevations that are relevant. So lots of different ways to determine the numerical value for this. Okay, so here's back to our first picture. And so now we see the equation. So static head is the difference, if there is a difference in gauge pressure, P4 minus P1, if they're both open to atmosphere, then P4 and P1 would be equal, and that term would drop out. But anyway, we're assuming that we're measuring these pressures in pounds per square inch. And so if we multiply that by 2.31, that converts PSI to feet of head for standard water. And then if it's not standard water, if it's either different temperature water or different fluid, we would adjust by dividing by the specific gravity of the fluid. So that would be the part of the static head based on the differential pressure between P4 and P1. Then we also have the differential elevation, which is the term Z4 minus Z1. And they're just measured relative to probably the floor, but an equal, the same datum will work, okay? So we're kind of showing the same thing here. We put some numbers on pressure. We're saying P4 is 20 and P1 is 10. So we have some numbers to plug in there. Here, we also have the elevation difference. So the P4 minus P1 is 10 PSIG times 2.31, 23.1 feet. And the elevation difference is 40 feet. So we add those together and we get a total static head of 63.1 feet. So I think that should be fairly clear to you. Okay, or we can go to PSAT. This is actually the pump head calculator, and we're kind of tricking it into calculating the static head. So if you look at the aqua blanks, those are the inputs. So we put in the same pipe diameter, which would be 10 inches on suction and discharge. We put in our gas overpressures, excuse me. On the suction side, it's 10. On the discharge side, it's 20. And for the elevation head, we just make sure that the difference between the suction and discharge is 40 feet. So we put in 0 for the suction gauge and 40 feet for the discharge. So that gets us an elevation head of 40 feet. We don't really have flow in this situation, so we put in 0 for the loss coefficients on the suction and discharge. And yes, dear. Can you talk? Well, I'm recording a lecture. Okay, go ahead. I'll call you back. Okay, I'm sorry. That was a call from my wife. Okay, so this totals up to the 63.1 feet that we had previously. Okay, so now we're going to move on to the pressure information. We've got a discharge gauge of 53 PSIG and a suction of 12.6. In this case, we're allowing the suction line to be 16 inches and the discharge line to be 14. And they're Schedule 30 stainless if you wanted to really look up the IDs. And now we're going to plug this into the PSAT head calculator, which is what it's really meant for, is to calculate the head on an operating pump. That previous example was just kind of tricking it into do a static head. So for the schedule, what was that? Schedule 30 stainless. If you look up the actual IDs on the pipe, on the suction pipe, you get 12.25 inches, and the discharge 13.25. We put in our gauge pressures, 12.6 and 53. The discharge gauge is 1 foot above the suction gauge, and we have no fittings in between the gauge and the pump connections. So we got a 0 on the suction line loss coefficients and a 0 on the discharge. Line loss coefficients, specific gravity 1, it's standard water, and the flow rate is 3,000 GPM. So you can see the calculated head, the differential elevation between the two gauges, 1 feet, the 53 minus 12.6 PSIG times 2.31 is 93.36. Differential velocity head is the V squared over 2G in the discharge pipe minus V squared over 2G in the suction pipe. That's 0.33, and that's all we got. That adds up to 94 about 94.6 or 94.7 feet. Okay. This shows from PSAT how to use the system head calculator. And so we've got an example up there. You see up on the upper left, 0.1 is input now at 3,000 GPM at 94.7 feet. And the second point is 0 GPM at our static head 63.1. Up above that, we input the specific gravity. This is standard water, so it's 1. And the exponent in our equation, we're going to use 1.9 here. And so that's all you got to put in. And we see the static head is 63.1, because that's what you get at the 0 flow point. And then the loss coefficient K prime is calculated to be what, 7.81468 times 10 to the minus 6. And so that's what we need to fit that equation. So it's pretty simple. Just get your two operating points, put them into the calculator here, and it spits out basically the equation for you. Oh, excuse me. So that's what the curve looks like plotted out. And out of PSAT, you can dump this to an Excel file. If this aqua box down here that the black arrow is pointing to, if you click that, then the result, this shows up in an Excel file. Or, you can take the equation and program it yourself. It's not very difficult at all. Okay, so, where do pumping systems operate? At the intersection of the pump and the system curve. So here we're showing the system curve in red and the pump curve in, I guess that's yellow. And so, excuse me, the operating point looks like it's about 2,500 GPM. I don't know, 86, 87 feet of head. Okay. Okay, so this figure shows the difference in system curves by changing the exponent from 1.9 to 2. So you can see it doesn't really make a whole lot of difference. The people I've worked with recommend 1.9, but theoretically, people expect it to be a squared relationship. So you could use either one. I don't know that there would be any reason to use another one, but one of those two would be fine. Okay, so remember that some things in the process can change and affect the system curve. The static head variables that can change the gas overpressures in the tanks. There's no assurance that that's going to be constant. It could vary, and that's going to vary your static head. The levels in the tanks could change. That would vary your static head. And maybe the temperature of the fluid and its density changes. And so the specific gravity changes, and that will affect the static head. On the dynamic side of things, you can certainly have a modulating control valve that could change, and for every valve position, different valve position, you would get a slightly or maybe significantly different system curve. Viscosity of the fluid can change. We can have corrosion, scale build up in the pipe, and we can have a strainer or filter that gets plugged, and that changes the overall resistance of the system. Or we could do actual changes in flow path. We could alter the piping system, and that would certainly change the system curve. Okay, but why is it important to consider a system curve at all? Well, because we got two important curves, and system curve is one of them, the other one being the pump curve. So it's fundamental to everything we do. Uh, First thing we should do in any pumping system optimization is to ask whether we can change either the system curve or where we're operating on it. Uh, and often we'll see that the real world is significantly different than what the world that the designers see using their generic loss coefficient. So the actual system that's designed and built may be considerably different in terms of flow and required pressure from the one that the designer intended. Okay, so each system has its own unique system curve. Here we show three different possibilities. The red curve that starts out at 0, 0, that's what we would call a closed system or a zero static head system. The dark blue curve in the center is a system that has significant static head and also some frictional head. And then the kind of aqua curve on top is what we would call a static dominated curve. It has 135 feet of static head, and at 4,500 GPM, the head only rises to 141, so it has very little friction, frictional effects as the fluid goes through the piping system to deal with. Okay, so all three of these curves were set up and fit to go through a common point of 4,500 GPM at 141 feet of head. Okay, pump curves. There are at least four types of curves that are given on the pump curves to characterize the operation of the pump. And these are versus flow, so it would be head versus flow, shaft or brake horsepower versus flow, efficiency versus flow, and net positive suction head required to avoid cavitation versus flow. Okay, so for a second, back to Bernoulli. And so this, we're going to write Bernoulli just across a pump. And so we've got on the top equation starting from the left, we've got the kinetic energy or the velocity head going in, V1 squared over 2G, plus the static or bursting pressure in the pipe, P1 times 2.31 divided by specific gravity. And we have potentially elevation head, okay? So that plus the pump head, so that's the energy that's coming in. Then we're going to put in additional energy in the pump, which is the pump head. And all that energy is going to appear at 0.2 downstream, which is velocity head V2 squared over 2G, 2.31 times P2 divided by specific gravity, and the elevation, Z2. So you can just rearrange the terms a little bit. You get the middle equation, which is kind of an equation for pump head. That's pretty much what the PSAT pump head calculator was doing. The only addition is the PSAT lets you put in some loss coefficients on the suction and discharge side to account for any fittings, any fittings or anything else that might be in that flow path before the suction or discharge flanges between those and the gauges. Right? So here's an example of just looking at some pump curves. There's different types of pump construction and different shapes of curves. So you really, if you start working on a given pump system, you need to get the manufacturer's curve so that you understand at least, how the pump is supposed to operate. These are shaft power curves. For the three pumps, you see they have different shapes. Some curves, like I guess that green one, continue to increase over the entire flow range. Others, not so much. So, you don't, until you pull a curve from a manufacturer, download one, you're never quite sure exactly what they're going to look like. There's our efficiency curves for 3 different pumps. So if you know a flow rate, you can read up and over to the curve and determine your pump efficiency. Okay, pump manufacturers provide performance curves in a variety of ways. So I have some examples here of what some of those might look like. I think this is a FlowServe pump. It was a Worthington, and FlowServe bought out Worthington. But anyway, so what you see here is you see 3 different pump curves, and we see that well, here, let me do this. I'm going to do something else here so I can get a pointer going here. Just a second. There we go. Okay, this is better. So up here for this particular pump, we see 19.49 inches max. That's the maximum impeller diameter that this particular pump casing can handle. Likewise, the minimum is, what is that, 15.83. Okay, yeah. This pump has been selected slightly off of the max for 19.25 rated, and the little triangle shows the rating point. So this looks like 4,500 GPM at about 141 feet ahead. So that's what we've been working with. So we see these curves are for 1185 RPM on a single stage pump. There's the pump model number. This sweeping curve would be the efficiency of the pump. So you can read up to one of the pump curves, whichever one. I guess it would be this one in the middle, and then that will give you the flowing head for that point. Okay. This is the minimum impeller diameter, and this is the net positive suction head required in order to avoid cavitation. So we'll talk more about that here in just a little bit. Okay. Let's see. We could make that. Can we bring it down? That's probably better. So this is pump 2. This is a different pump, but we get similar type information. So you have flow down here on the X or horizontal axis, and GPM. I'm sorry, this is flow GPM down here, and this is feet of head over here. I'm getting sleepy. Okay, so as a function of the flow rate, you can read the efficiency, and the efficiency is read over here on this axis. So that's the pump curve, or that's the efficiency curve. This is the actual pump curve, so this would be the maximum impeller. This is the one that got selected at this point, and this is the minimum impeller diameter. This, I didn't mention this on this previous slide. Oops. Here. MCSF, that's minimum, I think, continuous standard flow. Is that right? Something like that. That's the minimum flow. That's the minimum continuous steady flow, something like that. I'm forgetting, but anyway, that's the minimum flow that you should operate this pump. If you operate to the left of it, it's going to not be good for the pump and not probably going to be terribly stable or efficient. So some manufacturers put those lines on there and some don't. You see it here, they don't even tag it. They just put that little line back there and you're supposed to know what it means. Okay, so down here on the bottom, we're reading horsepower over here. So here's your horsepower curve as a function of flow rate. And here's your net positive suction head required to avoid cavitation in the pump. And it's a function of flow, and it can be read over here on this axis. Here are some ISO efficiency lines. Most of the pump curves will indicate the efficiency at any particular operating point. You can read it off of the curve. And so this one's pretty well selected. That's my selection point. This is my highest efficiency ring, and I'm inside of it. So that would be a pretty darn good selection if you can get one like that to work out. Okay, then we can put shaft power curves. You see the different horsepowers, 10, 15, 20, 25. And so, you pick your GPM here at 450. Up in here, I'd say we need to probably have a 20 horse motor, maybe a 25 or 30. If you want to make sure that you cannot overload the motor, I mean, if this thing starts falling way off over here, it's possible that you may be able to overload the motor. These are the ISO tolerance bands on these various curves. So you see they're not even required to be completely correct, or they allow some wiggle room in what's published. So you get some kind of an idea of how much is allowable before they could be forced to retest or come up with an additional set of data for a particular pump. This is a vertical turbine pump. It extends on a shaft vertically down into what we call a well, a hot well or a cold well. And the impellers are on this shaft. They're called bowls, and they force the water up. Most of these are 2, 3, 4, 5 stages, and there's some notes in here about how to use the chart to determine efficiency with different numbers of stages of pumping. So you should look over that. That's a pretty good curve. Okay, so here again, we're saying where do we operate at the intersection of the pump curve and the system curve. So you guys know that. Okay. And guys, I'm tired. I'm gonna post this, and I'll send another link to another video, and I'll try to get another posted in a day or two to you. So I hope you guys have a good night. Thanks.